Hi, so this is a lecture for you to watch while I'm gone on Friday, and we are going to be starting chapter 24 and talking about electromagnetic waves, or light. So just to review what we had done on Wednesday, we had introduced the idea of the forces between two current carrying conductors, or two current carrying wires as an example of that, and saw that when we had two currents that are moving in the same direction, that resulted in an attractive force, because this one had a magnetic field pointing out of the board over here, which then V cross B, or rather Li cross B, ended up being such that the force pointed to the right for this current, and then this current created a magnetic field that actually pointed into the page over here, and then the I cross B for this wire interacting with the field of this wire ended up having a force pointing to the left there. Of course, this exactly flips when we flip one of those wires. Now that flips the direction of the magnetic field produced and the force as well. So then we end up getting a repulsive effect when we have two currents pointing in opposite directions. And you can work out the right-hand rules of that as well. So then what we want to do now is kind of combine a lot of the ideas that we've done up till now. And I'm bringing up the concept of Maxwell's equations. Now, these equations are a little bit more mathematically rigorous than what we're prepared to deal with in class, but I wanted to briefly put up some of the math here, which you don't really need to understand, but bring out the meaning and how it connects to everything we've studied so far. So the first of these equations that are grouped together by Maxwell, the scientist synthesized a bunch of work from other scientists and kind of put all the pieces that other people had worked on together to form a theory of electromagnetism. So we're combining the ideas of electric fields and magnetic fields and those forces, and we're putting them all together in one. The first idea was Gauss's law, and we saw this when we talked about the electric fields coming from positive and negative charges. What Gauss's law really tells us is that any electric field line has to come from some positive charge, and if it is going to terminate, meaning end, it does so at a negative charge. So that really just means that a positive charge has electric fields pointing away from it, and if this were a negative charge, all of those electric fields would be pointing towards the negative charge. So we've seen that idea before. This is just a mathematical way of talking about it. The next idea is kind of a Gauss's law for magnetism, if you will. It's the idea that we can't do this Gauss's law thing where we have electric field lines coming out or going in to just a single point with magnetic fields, because magnetic fields don't have just monopoles. They always come in a north-south pair. So the magnetic monopoles don't exist. That's part of this second equation, and that all of the field lines come out of a north and go into a south, and they do so kind of in a continuous fashion. They don't just kind of go out and stop. They always go back and come back to the South Pole if they leave from the North Pole. That's the second equation here, called Gauss's law for magnetism. The third of four, so we're halfway there now, the third of them is called Faraday's law. And this is the fact that any changing magnetic field actually induces an EMF, or a electric field, and some change in potential. And whatever that changing magnetic field is, this EMF that it produces acts to oppose the changes in B. Now, we haven't necessarily seen this per se, but I want to show a demo right now. So, but before I show it, I want to briefly explain what this is, and this is the mathematical way of saying it, but really this is saying there's some changing B and it means that there's going to be some electric field that results in that. But this is kind of a picture of what we might see. So here is basically a solenoid, right? It's a wire wrapped in many, many loops around. And in this case, when we bring a permanent magnet near this, the magnetic field here is going to interact with this loop and actually drive current in here because it's producing an electric field. It's actually causing charge to move through this wire. And then that will end up creating a magnetic field that actually resists this magnet. So it's going to actually, if we tried to push this in, there would be a little bit of a force pushing back because this would create a little electromagnet because we're moving wire or moving current through a wire, and that we know results in a magnetic field, that the loops of wire all produce little pieces of magnetic field. The more loops we have, the stronger that field, and that would produce a little north pole here, which would act to push on this north pole of the magnet as we brought it in. So it resists the magnetic field of this permanent magnet as we bring it in. Now, also, this would do the same thing if we tried to pull this magnet away. So say if we pull this magnet away, it wants to, we'll drive current the other direction in this case, and we'll end up seeing a magnetic field produced there as well because we're driving current, because we're creating an electric field by varying the magnetic field at this location. So that isn't super intuitive, right? But I have a kind of a demo that we can see. And first I'll talk a little bit about it, and then I'll have you pause and actually swap over to the other video I posted on Moodle. But the idea is that if I take a magnet, and this is a copper tube here, that is, it's not actually a magnetic metal. This is not like iron. We know iron will stick to a magnet, but copper doesn't do that. But it is conductive. Copper is great at conducting electricity. So if I take this magnet, if I just hold it up to the side here, it's not going to attach. It's not going to stick to this pipe. But if I drop it through the pipe, as it falls, the magnetic field of this magnet is constantly going to be moving through this pipe. So any location in the pipe is going to experience a changing magnetic field because it's obviously the magnetic field is stronger the closer we get to one of these poles. So like down here right now, I'm sorry, that's my dog. Super boy, come on. The magnetic field down here from this magnet is not very strong, but right here it is. And so as the magnet falls, the magnetic field is going to be changing constantly throughout this. And we're going to be driving current because of that changing magnetic field. And that changing magnetic field, that current, produces... Oh gosh, sorry guys. So, sorry, I had a package dropped off and my dog was very upset at the doorbell ringing. So, as these currents get driven through this pipe, they produce a magnetic field. That magnetic field actually acts against the direction of this magnetic field. So we get a north towards a north, and it actually puts a force upward on this magnet. So gravity is pulling it down, but the magnetic field is pushing it up somewhat. So it actually falls slower than it normally would through the pipe. It actually takes quite a while to fall through the pipe, depending on how strong that magnet is and how strong those currents will be. Of course, if it ever came to a complete stop, it would start falling again because the currents would go to zero and gravity would win. So it never can stop falling. So go now, pause the video, go over, take a look at that other video I posted where I do this example. Then come back. Okay, so I'm assuming that you've watched the video now and seen my explanation for a second time. So that's Faraday's law in action. It's actually sometimes called, this application of Faraday's law is sometimes called Lenz's law. So now, the last of our four Maxwell's equations is Ampere's law. This is definitely one we have seen before, in that a moving charge, or a current, produces a magnetic field. So we saw this when we talked about wires and forces that acted on wires and things like that. So the meaning of this is magnetic fields are generated by moving charges or by changing electric fields. So that is exactly what this says. This here is something about creating magnetic fields, and here this J is really the I that we've seen for current, except this is talking about it in terms of the density of current. So this is charge density, or current density, I should say. We haven't really talked about how this can also happen when we change any electric field. It can also produce a magnetic field. Okay, so those are Maxwell's equations, and you do not need to know the mathematical expressions of this. But these are ideas that we have talked about to some extent in this class, and these really show that these equations really show that these are not separate ideas. They're actually all aspects of the same thing. They're all aspects of the electromagnetic force, and these mathematical expressions allow us to predict how the electric field and the magnetic field change over time, and how do they interact with each other, how do they interact with charged particles. And so it's really it's a good descriptive theory that is very well accepted at this point of this is how electromagnetism works. We have a very good handle on electromagnetism, especially in comparison to some other fundamental forces. So one interesting thing about these equations, though, is they tell us how these fields evolve. They also tell us what happens if maybe things were to, say we know how a charged particle and its electric fields would look. So if I briefly just draw in a particle here, and maybe it's a positive particle, so we have, these are its electric fields pointing outward. What if I shook that like this here? If I shook it, then these electric field lines would then have little wiggles in them. And those wiggles would want to move outward because, I mean, say I just shook it and I left it up here, and eventually it would want to just look like this again. But these vectors are somewhat different than these vectors because they're starting out at a different spot. So if I shook it up and down, we would kind of oscillate between vectors that looked like they're coming from here and vectors that look like they're coming from here, and maybe something in between. So what we end up getting is we get these little wiggles in the electric field, and they have to go somewhere. They have to go out into the universe, and they don't happen instantly. In fact, Maxwell's equations tell us that they move out at this speed. So this is that weird magnetic permeability of free space, and this is oh gosh, I always forget the names of these because they sound so similar. Permeability and there it is. Permittivity. So permeability and permittivity of free space. So yeah, they're weird. They have very similar names, right? But they combine together and they tell us something about the speed that these things would propagate outward. And that speed, there we go, erase all that. Is actually the speed of light. So that's what we're actually talking about here, is the speed of light is that this is the speed of light, and this is how fast that this propagates out. So really what we're talking about when we talk about oscillating fields, we're talking about light. that the electromagnetic oscillations are light. Now, with this idea of the speed of light, we can talk about if how fast things propagate through, how fast signals of light propagate through vast distances. Of course, in our everyday lives, it's so fast. It's this 3 times 10 to 8 meters per second. That's 300 million meters per second, or 300,000 kilometers every second that light can travel. But if we want to talk about vast distances like in astronomy, say Earth and Mars are sometimes only, and I mean only, 9.6 times 10 to the 10 meters apart. And when they're farthest apart, they're actually 4 times 10 to the 11 meters apart. So this is a huge number, right? But in each situation, how long would it take for a signal, of a data signal, which we're going to send from some form of light? We're going to beam it, like radio waves, perhaps, as we'll talk. Radio is a form of light. And we're going to beam data maybe from the Perseverance rover that's on Mars back to Earth. So if it's at its closest, well, we know that, grab my pen again, that the distance something moves is going to be the speed times some amount of time. Here I'm using c for the speed of light, and the distance it's going to travel would be d, and it's going to take this amount of time. So then, let me just say t is d over c in this case. And so if we know the speed of light is always going to be 3 times 10 to the 8 meters per second, then we can say, well, the time it'll take, 9.6 times 10 to the 10, divided by 3 times 10 to the 8, that's 320 seconds in that case. So it takes 320 seconds just to send a signal one way. So that's 5.3 minutes. Or 5 minutes and 18 seconds or so to send a signal from Earth to Mars when they're at their closest. When they're at their farthest, we would get 4 times 10 to the 11 divided by 3 times 10 to the 8 meters per second. Then it's closest to, then t, when they're at their farthest, is 1330 seconds. And that is, let's see, about 22 minutes or so to travel. So light is not instantaneous. It takes some time. So if we have the Earth over here and Mars is way over here on the other side of the sun, it takes 22 minutes to cross. But when we're really relatively close by, like this, it only takes about 5 minutes or so for that signal to propagate. So this oscillating electric field that we're talking about, it comes along with an oscillating magnetic field. This is what one of Maxwell's equations told us, that whenever you have a changing electric field, you're going to have a changing magnetic field along with it. So these things are oscillating together. And so that's what we have here. So we've got maybe red is your electric field and blue is your magnetic field. They oscillate up and down together, and that is what light is. It's an electromagnetic wave. So here's another example of this where you can actually see those oscillations a little bit better. And you can actually see that they're what a physicist would call in phase with each other, meaning that E reaches a maximum up here the same time B reaches a maximum. And they're both zero at the same time. So they're oscillating up and down, just like sine waves or cosine waves, and they are in phase, meaning they both reach maximums and minimums at the exact same time. There's a few other things to notice about this, though. One is that they're always exactly perpendicular to each other. So here we have E and B are oscillating. E is going up and down in the y direction in this graph. Here's y on the vertical, and E is going up and down like that. B is going side to side in the Z direction. And together, these waves are moving from the minus x direction to the positive x direction. So they're also moving in the direction perpendicular to both E oscillations and B oscillations. So the E and B oscillate together, and the wave, the light, is actually traveling perpendicular to either E or B. And so they oscillate in the direction perpendicular to the propagation direction of the wave. And light is this type of wave, we call it transverse, meaning that the oscillations themselves are not in the same direction that the wave is propagating. So a transverse wave, this is like if you had a string or a rope and you were swinging it up and down. The wave that you make as you swing it up and down travels along the rope. It doesn't, and the oscillations themselves are up and down. They're not in the direction that that wave travels. They're perpendicular to each other. So that's what we mean when we talk about a transverse wave, and light is a transverse wave. So when we say light is a wave, that means it has a bunch of properties that we should talk about. That means it has a wavelength, meaning how far in physical space does it go from one node here, where it's at 0 amplitude, all the way to another, goes all the way up and all the way back down and back to where it started. This would be one full wavelength, because we have to go from up to down and back to where we started for it to be one full wavelength. That is something we would usually write with this Greek letter lambda, and that's the wavelength of our wave, or of light in this case. We also have a frequency, meaning how often does one of these peaks pass us by. So we could count, and if we watch this wave pass us by, or maybe I go back to here, I could count. Let me put my cursor right here and say, okay, there's a peak right there, and there's a peak right there, and I could count how frequently does that happen. How many times per second, or how many times per minute does that peak pass me by? That's what we mean when we talk about frequency. So there's wavelength and frequency. There's also an amplitude. This peak has a height to it, and that height might be different for different waves. The other thing about the amplitude is that we have two waves here. They're in phase with each other, but they each have their own individual amplitude. So we have an amplitude for the electric field here in kind of this yellow gold color, and we also have a magnetic field oscillation that's going to reach its maximum at the same time that this reaches its maximum, but it's going to be a different amount, or a different amplitude. So we'll have some amplitude of the magnetic field measured in Tesla. We'll have some amplitude of the electric field measured in newtons per coulomb, or volts per meter. And the wave propagates with some speed. Now, we actually can relate the speed of any wave to the wavelength and the frequency, because if we know that this many wavelengths pass us by every second, say we have 5 wavelengths passing us by every second, that means that the wave is propagating 5 times that wavelength per unit time, or per second. And so we just need to multiply the wavelength times the frequency to get the speed of the wave. And this, again, that speed of this wave for light is always going to be that 3 times 10 to the 8 meters per second for light. That's just the speed that light travels. And the actual amplitudes of E and B, we would usually write the amplitude as some E with a 0 next to it, or E naught is usually how we would say this, and B naught would be the amplitude of the B oscillations. And they are actually also related by this C, that E over B is equal to C. So if we wanted to say the amplitude of E naught, is actually C times the amplitude of B naught, if I just multiply both sides by B naught. So generally, since C is such a big number, the oscillations of the electric field tend to be much bigger than the oscillations in the magnetic field in terms of just the amplitude and those numbers. So just as an example of the types of calculations we can make with this idea of oscillating magnetic and electric fields, if we talk about the amplitude of the E oscillations from a light source with this B, so this is, oh, sorry, let me erase that real quick. So if this is our B, it's oscillating in time because we have a sine component here. This thing in front of the sine tells us how far these are oscillating in this direction. So this is our B amplitude. So B naught is equal to 1.2 times 10 to the minus 7 Tesla, just because it's this thing in front of the sine. So if we want to know the amplitude E naught, based on this, it would be C times B naught, and that's going to be 3 times 10 to the 8. So 3 times 10 to the 8 times 1.2 times 10 to the minus 7 is about 36, and that would be newtons per coulomb electric field. So that would be the answer to this first one, that we know the E oscillations would be related to the B oscillations by this, and so we could figure that out. What's the frequency then? The frequency is going to be related to whatever is inside here. So usually we would write out this equation like B as a function of T. I'm just rewriting this equation to make it a little bit more formal, as some amplitude times sine, and inside the sine we would go 2 pi times the frequency times the time. And the reason why we write it this way is because we know that sine repeats every time you go around the unit circle, meaning that you've gone 2 pi radians around. So whatever goes inside here, I know we're used to writing it as in terms of degrees, but here we're always going to be thinking about it in terms of radians when we think about it this way. I know that that's not always how you guys are going to be used to thinking about this, but it's kind of required at this point to think in terms of radians. So 2 pi radians, this is basically 360 degrees. So we've gone around one full oscillation. But we do that every time the frequency times the time is equal to 1 in this case. So if the frequency is, say you have 5 hertz. Hertz is the unit for frequency. It just means per second. So 5 times per second this wave passes you by. That means in 1/5 of a second you would have gone through one wave. And so F times T would be 5 times 1/5, and you'd get 1 there. So all this to say is that here we have 2 pi F where this 1.26 is. So 1.26 has to be 2 pi F. And in this case, if I then divide 1.26 divided by 2 pi to find the frequency is 0.2, or 1/5 in this case. So the frequency of light is 0.2 hertz. So 0.2, and we would write that as a capital Z, or capital H with a lowercase z, like this. Got a little messy there. Now, then we could say, okay, well, if we know the frequency, what is the wavelength? And here we can use the relationship between wavelength and frequency like this to tell us the speed is equal to those two, wavelength and frequency multiplied together. So we could solve that for the wavelength and say that's c divided by f. And if we take that, that would be 3 times 10 to the 8 meters per second for c, divided by f, which is 0.2. And this wavelength is huge. It's 1.5 times 10 to the 9 meters. So to have something with such a small frequency, you need such a huge wavelength for light. So most light has a much higher frequency than this and a much shorter wavelength. And then we could think, okay, what time? Because we know if we're watching this, and maybe we start right here and we see what time does B reach its first maximum value? If we start from t equals 0, sine of 0 is 0. So we would need to go up to here, which is 1/4 of one full oscillation. And we know that it takes, or we have 1/5 is our frequency, so we have only 0.2 waves pass us by every second. So we'd need to wait 5 seconds to get one full wave. So I could say that the period, which sometimes we use tau to tell us how long does it go from one end to the other for one wave, is 5 seconds. But I want to know how long does it take B to go from 0 up to the maximum, and that takes only 1/4 of the full wave to go from 0 to the maximum value. So the answer to this one would be sum t equals the full period divided by 4, because I can say here's 1/4 of the wave, there's another fourth when it goes back down to 0, another fourth when it goes all the way back up here, and then finally one more fourth to finish the whole oscillation. And so this would tell us the first time B reaches its maximum value is 5/4 of a second, or that would be about 1.25 seconds. Okay, so those are some kinds of calculations that we would be able to make understanding the wave-like properties of light. But there's a whole lot of other important consequences to treating light as a wave. One is that when we think of light, we think of maybe different colors or brightnesses and things like that. Well, color is very related to wavelength. All these different colors we see actually have different wavelengths to them. Red actually is the longest kind of light that we can see with our eyes. And violet or purple is some of the shortest wavelength light that we can see. And in between we would have the whole rainbow. In fact, the reason why we can see rainbows and the reason they're in the order that they are is because light will as light from the sun hits kind of water droplets in the atmosphere, it actually spreads out depending on its wavelength, and just like a prism. And so that's why you end up seeing them in this order, this kind of, if you want to go Roy G. Biv or whatever, in this order. We see that show up whenever we have a prism that splits light like that, and that's why we see rainbows. But beyond just the rainbow of the visible spectrum, there's lots of other kinds of light. We're going to talk about all the way from radio waves, which are the longest wavelength kind of light that there is, all the way up to gamma rays, which are the shortest wavelength. That the wavelengths of these are on the order of the size of the atomic nucleus. And then everything in between, from microwave, infrared, visible, ultraviolet, and then X-ray and gamma ray. And we'll talk about exactly what all is going on here, but there's so many different kinds of light, and we use them in a lot of different ways. And we would call this the spectrum, the electromagnetic spectrum. Here's another way of looking at that, where we can see wavelengths and frequencies. So here we can see that a lot of this light, in fact, visible light, for example, has frequencies in the kind of 10 to the 14 hertz regime, and something in like the 10 to the minus 6, 10 to the minus 7 wavelength regime in terms of meters. So we're talking very, very relatively short. So we're talking about maybe microns or nanometers kind of wavelengths, and we're talking about, what would this be? So this would be gigahertz, megahertz, gigahertz, terahertz kind of regime in terms of frequencies. You can kind of see how some of these things kind of have some fuzzy boundaries, overlap, maybe where radio waves, microwaves, and infrared kind of in this regime, you don't really know. You call it one or the other depending on what context you're talking about. Same thing over here with gamma rays and X-rays and UV, but so there's some kind of fuzzy boundaries, but so there's definitely kind of an ordering in terms of which ones are generally considered longer wavelength or shorter frequency than the others. And now I just want to talk through some contexts of all of these different ones. So radio waves are the longest wavelength and have wavelengths that can go from centimeters to many, many kilometers. They're very low energy, and they don't really have any major health risks associated with them because they're low enough energy that they can't really do much to your cells of the human body. Of course, we'll see how that changes once we go to higher energies. We know radio waves from like music broadcast, television broadcast, things like that. Of course, you might know AM versus FM. Those are actually different wavelengths associated with those broadcasts. If I go back here, you can see AM radio is actually a much longer wavelength than FM radio. And it actually has a shorter frequency. So we know frequency and wavelength are inverses of each other. So when we go to very long wavelengths, we're at short frequencies, and very tiny wavelengths are very big frequencies. So these AM radios are longer wavelength than FM radios. As a result, they interact differently with our atmosphere. Now, most radio will travel directly through our atmosphere, but AM radio waves will actually interact with a layer of the atmosphere called the ionosphere, and that will actually cause them to kind of bounce back towards Earth. This is actually a benefit for radio stations. If they want to be able to send their signal even further out, they can have the AM stations can bounce to areas that FM stations wouldn't be able to reach because they're able to bounce off the ionosphere and travel even further around the curvature of the Earth even. And the other important piece, at least for me, because I am an astronomer by trade, is that radio waves readily, or most of them, go through the atmosphere. So I guess not these AM radio waves, but a lot of other radio waves will travel through the atmosphere. And as a result, we can study distant galaxies with radio. So here, these features that are kind of going perpendicular. Here's the galaxy itself. Here you can see dust and gas inside the galaxy. Here And this emission coming out perpendicular to the kind of disk of this galaxy is actually radio waves that we're seeing. And this is actually very much related to the stuff that I do research on. This is called a radio galaxy because it has these powerful jets of radio emission coming out of the center. And I do simulations to model these kind of galaxies. So yeah, there are lots of natural phenomena that emit radio waves, so it doesn't have to come from a radio transmitter on Earth. And this stuff is not coming from some alien sending out a radio signal. It's coming from just high energy particles and magnetic fields and some physics that we're not prepared to talk about at this point. But it's all natural processes. Another very useful case for radio is, you've probably heard of radar. Radar is radio detection and ranging, at least that's what it was originally named that way. And it's basically, we can say, it's kind of like sonar, if you've ever talked about like how bats can see their way through by kind of putting out high-pitched chirps and things like that. If we send out a radio pulse and it bounces off of some distant target, and we detect that echo, that returned pulse, after it bounces off that target, we can figure out how far away it must have been, because we know how fast radio waves travel. We know they travel at the speed of light. So the distance to some distant object, well, c delta t being how long since we sent out the original chirp and how long it took to come back, c delta t would be the total distance there and the distance back. So it's twice the distance from us to the target. So we would just divide by 2 to tell us what's the distance between us and the target. And so we can calculate exactly how far away something is by using radar. So that's a bunch of different applications of radio. Of course, we can go down to shorter wavelengths and talk about microwaves. Of course, we have, probably all of us have one of these in our homes where we can use microwaves to heat up food. What's actually happening there is the water molecules that make up your food, if we send wavelengths of that are frequencies of radiation into the microwave oven, that will kind of resonate and make these polar molecules align with the electric fields that we're putting into this oven, then they will kind of oscillate back and forth within the food, and that actually creates a lot of friction. And actually, the water molecules are absorbing this energy from the electric field. They're moving around, and they're actually just rubbing together, and that heats the food from within, just from the friction of that motion. And so we end up cooking the food from inside rather than from just heating up the interior of the oven. We're actually heating the interior of the food by running electromagnetic fields through it and causing it to move around within the food and heat it from within. Going to even shorter wavelengths, higher energies. This is just now just a little bit below in terms of wavelength what we could see. So we call this infrared radiation. So it's just a little bit longer wavelength, a little bit longer wavelength than what we can see with our eyes, but it's still a little bit shorter wavelength than like the microwaves we were just talking about. This is the type of radiation that most objects here on Earth would be emitting because of what temperature they are. So just like the sun is glowing bright because it's a very hot ball of plasma, we all glow as well in the infrared. This is actually a picture that I took of myself. Actually, it's a reflection of myself in the infrared. So this is me holding up a piece of glass in a frame, just kind of like an old picture frame, but there's nothing in it besides just glass. And glass actually is great at letting visible light through, which is why we make windows out of it. but it's also great at reflecting infrared radiation, which is why it's you don't have to do a ton of insulating of your windows per se. Of course, you have to insulate around the windows, but the windows themselves don't let a ton of heat out because they're good at reflecting infrared radiation back towards you. So here I have an infrared camera that I'm holding in my hand here, and I aimed it at this, and I took a picture of myself back in 2014. I had to dig out that photo. And so really what we're looking at is just heat that we're looking at. And that this heat is a form of light that's being emitted by different objects, and in this case reflected by this glass back towards me. So we all glow in the infrared. Another interesting phenomena that we want to talk about with infrared radiation is the greenhouse effect. Of course, the sun emits energy across the whole electromagnetic spectrum, but a lot of it comes out in visible light. That visible light comes down and comes through our atmosphere, because it'll come pass through without being absorbed or anything. And then maybe it gets absorbed at the ground or reflected or whatever. But a lot of that gets absorbed by the ground and then maybe heats up the ground. And then, of course, the ground radiates that heat in the form of infrared radiation. And greenhouse gases like CO2 or H2O and all those things in our atmosphere are really good at reabsorbing and re-emitting infrared radiation. So it kind of acts as a blanket, holding that infrared radiation in and causing the Earth to be warmer than it otherwise would have been. Of course, this is actually a very good thing because our planet would be very, very cold, much colder than it is now, if we didn't have any greenhouse gases in our atmosphere. But of course, if we add too much greenhouse gases by polluting our atmosphere and adding a lot of other hydrocarbon compounds into our atmosphere, burning fossil fuels, then we increase this effect. We trap more and more heat, and we disrupt the balance and cause our atmosphere to heat up more and more. And this is what global warming and that runaway greenhouse effect is all about. So, in fact, this is, if you want to go and look at an astronomy case, Venus is so hot we would not at all be able to survive on the surface, hundreds, thousands of degrees on the surface, and it's coming all from the fact that Venus's atmosphere has so much carbon in its atmosphere that's acting to absorb and has a crazy runaway greenhouse effect that's trapping way too much heat. So moving beyond infrared, we get to finally the visible part of the spectrum. So we've kind of been approaching from this side here. We went through the infrared, and now we're finally into the visible. Most of the sun's energy comes out in the visible, so this is actually kind of a rough graph of what the sun's energy output looks like. We have some energy coming out in kind of radio and infrared, but it peaks up here in the visible, and then there's some energy over in the ultraviolet as well. But because it peaks here, that's probably why our eyes evolved the way they did, and why we see visible light rather than maybe seeing light of slightly longer wavelengths. And we can look at how the wavelength of this light varies. Red is about 700 nanometers or so, and we can see from about that 700 nanometers all the way down to about 400 nanometers. And if it goes much shorter than that, we end up not being able to see out here in the ultraviolet. And also, yeah, let's see. Then going on to talk about ultraviolet, some of this ultraviolet will get absorbed by different layers of the Earth's atmosphere. This is why the ozone layer is very important, because this blocks a large portion of ultraviolet that would come down. And the reason we care about that is because this is now we're getting into the range where we're high enough energy and frequency kind of go hand in hand. The higher frequency you are, the shorter your wavelength, the higher your energy would be. And we're getting into the range where we're getting to high enough energies that this could be damaging to human cells. Of course, this is what sunburn's all about and why I need to put sunscreen on if I'm outside for long periods of time. And luckily for us, most of this gets absorbed by the Earth's atmosphere. Now, not all of it, of course, because we do still need to put sunscreen on in the very sunny days. But we would get a lot of this absorbed in the outer layers. This ozone layer is very important to block some of that, and this is why in kind of the late 80s, early 90s or so, when we were realizing that some of the pollutants that we were putting out into the atmosphere were actually causing damage to the ozone layer, there was actually a big international agreement to cut down on these CFCs, these chlorofluorocarbons. And so we changed what we used to produce various things, like, it was a lot of aerosols, like hairsprays and things like that. We changed what we used in those products, and we actually made a huge difference. And the ozone layer has recovered, and so it's a big win for science that we've been able to fix or allow Earth to recover from the damage that we caused by damaging the ozone layer. And this is a big success. Going to even higher energies, shorter wavelengths still, we're at almost to the end there, where we get to X-rays. X-rays are very high energy, and we're definitely in the range where we can cause real damage to human cells or any biology, really. You could cause cancers by having prolonged exposure to these. And because they're such high energy, they can penetrate right through your body. Now we can actually use this to our advantage. Of course, most people, when they think of X-rays, they think of medical imaging. So we can see through pieces of the body and see things that are denser, because the X-rays are going to be blocked by the parts of the body or anything within the body that is very, very dense. And so what we see is we'll see through the soft tissues, and we'll see these medical images like this pacemaker, or other wires and things that are connected within this patient, and we'll be able to see their bones, because the bones are higher density than the softer tissue, and so you could maybe see where bones are broken or things like that. But of course we don't want overexposure, so if you ever get some medical imaging done, it's a very it's as low of a dose as they can get away with, and they also will make sure that they're covering up different parts of your body, usually with like a lead apron or something, so that they're not irradiating you more than they should. X-rays are also useful in other contexts. Just generally, if you want to create an image of anything with say a microscope, the wavelength of the light that you are going to use to create that image needs to be smaller than the thing you're imaging. And when you get to really, really small things like proteins or atoms, which are only maybe some nanometers or even less than that in size, you can use X-rays, because they're so tiny in terms of their wavelengths. They're such high frequencies and tiny, tiny wavelengths that you can actually use them to image in like tiny proteins. So this is the first ever image that was taken of DNA. You can see hints of that double helix structure. This is the image that won a Nobel Prize. Unfortunately, it didn't go to the people who made the image themselves. This Rosalind Franklin and Raymond Gosling was a graduate student working under Franklin when he produced this image under her guidance, and of course then he showed it to some other scientists who wrote a paper on it and got the Nobel Prize. And of course that's one of the most famous examples ever of not correctly citing your sources and taking credit for other people's work in science. But this was an incredible discovery, and we used X-rays to image this DNA, tiny, tiny nanometer scale. Finally, at the very most energetic end of the entire electromagnetic spectrum, we get to gamma rays. And these are most energetic forms. They have very tiny, tiny wavelengths, huge frequencies. They're oscillating very, very quickly, up and down. And then these things are generally coming from some interactions with the atomic nucleus. Or maybe you have some photon, some little piece of light coming in and hitting an electron and bouncing off, and that can cause very high energy light as well. You can see how you can kind of use this in some ways to image, but this is just very dangerous to expose people to, so you have to be very careful with this. And I also include another astronomy kind of example here, that from the most powerful engines in the centers of galaxies, again, kind of connected to my research, these jets that come out, if they are aimed right towards you, you will see gamma rays from these things. They're called gamma ray bursts. And these are some of the most energetic things in the entire universe. So that's kind of a walk through the entire electromagnetic spectrum, and that's all we're going to do for today. So just to summarize what we've talked about, we took a little qualitative look. We're not going to go quantitative at all with these equations, but we looked at Maxwell's equations and just talked about what they meant. We also talked about electromagnetic waves generally. What does it mean for them to be a wave? What are those properties that they get associated with when we talk about them being a wave? So what is their speed? What is the wavelength, the frequency? What is the amplitude of those waves? And then we walked through the electromagnetic spectrum, starting at the long wavelength end, radio, and going all the way to the shorter wavelength end with gamma rays. And I'll just put this back up again to walk us through that. So we started down here, again, with very long wavelengths. This is millions of meters at this end, and very, very small frequencies, just a few hertz, a few times per second one of those waves would pass you by. And then all the way down at this end, when we get all the way up to gamma rays, we're down to well below the size of an atom at this point. Atoms are like roughly here in terms of their sizes, like in the nanometer, or I guess nanometers would be right in here-ish, and then we would get to that. An angstrom is a weird length unit that's 1/10 of a nanometer, and yeah, these things are tiny, tiny wavelengths, but they're enormous frequencies. Even visible light here is already near the terahertz regime, and then we get into, I don't even remember all of these metric prefixes because we don't use them that frequently, but just enormous frequencies for those. So that was our walk through the electromagnetic spectrum. So when you view this, homework 6 should be up Friday, and then next week, if you haven't done your quiz corrections and want to do quiz corrections, please reach out to me and we'll figure out a time to do it. And then we will be finishing off chapter 24. There's only a little bit left. This is a relatively short chapter. Next time on Monday, we'll finish off chapter 24 and probably even do a little bit of chapter 25. A week from this Friday, when you're watching this, the week right before, or the Friday immediately before spring break, we will have our quiz 2, so you can start studying for that if you haven't already. That'll be chapters 20, 21, 22, and 24. So 4 chapters worth of material. Similar structure to the last quiz in maybe a few questions, probably 3 questions still, I would expect. And do look at homeworks, exercises, and questions from the back of the textbook chapters as good examples of where to be studying for that. Otherwise, I will see you guys next Monday. Thanks for watching, and have a good day. Have a good weekend.